In this video, we will discuss the concept of analysis of variance with two independent variables instead of just one. One-way ANOVA, as discussed in the previous video, tests the effect of a single independent variable on a single dependent variable. That is, the null hypothesis in one-way ANOVA is that you have different samples drawn and that the mean of each sample is the same, that there is no significant difference between the means of the different samples. In this case, or in the case of one-way ANOVA, those different samples are usually affected with different treatments. For example, a sample, three different samples being treated with three different kinds of medications. In this case of two-way ANOVA, we allow for a second independent variable, such as perhaps we are not just measuring the effect of the three different medications, but we are also breaking it down by, say, gender, male, female. For the purposes of this, we use binary gender. Another example, one that we will use throughout this video, would be, suppose that we want to test the effects of certain types of plant foods as well as different soil compositions on plant growth. That is to say, we want to see if certain foods help the plants grow larger, and also if certain soil compositions help them grow larger. Now, we could do this as two separate experiments. We could do one experiment where we use the same soil composition and all different plant foods. And then we could do another one where we use the same plant food but all different soil compositions. Or we could find every combination of each, so that if there were, say, 3 different plant foods and 2 different soil types, that's a total of 6 combinations. We might lay out a table such as this. We might have soil A and soil B. And then we might have food A, food B, and food C. And this would allow us to have 6 different combinations we could have food A with soil A. We could have food A with soil B. We could have food B with soil A. Food B with soil B. We could have food C with soil A. And we could have food C with soil B. This gives us 6 combinations and allows us to test, first, individually, what effect the plant food is having. Second, individually, what effect the soil compositions are having. And third, does each one matter with relation to the other? That is there some kind of connection between them? Now, in order to do two-way ANOVA, we do have the same basic requirements as one-way ANOVA. One-way ANOVA had the requirements, first, that the populations that the samples are drawn from must be approximately normal or normal itself. Second, that the samples drawn are independent. And third, that the populations must have the same variance. Now, just like with one-way ANOVA, we will assume these things to be true. Now, in one-way ANOVA, it was not necessary for all the samples to be the same size. In two-way ANOVA, because of the complexity of it, it is a requirement that all groups must be the same size. So we have that new requirement. This requirement is new to two-way ANOVA. It did not exist for one-way ANOVA. That is a requirement for how we do this because of the nature of the calculations. Now, we will typically assume, as with one-way ANOVA, that the first three requirements are met for the purposes of this course. We also will only be in situations where the groups are the same size. So we will take it for the purposes of this course that all of these requirements are met automatically. As with any hypothesis test, there must be a hypothesis. There also will be a value for alpha and a test statistic. So we will start with the hypotheses. The hypotheses for two-way ANOVA, well, there are actually three sets of hypotheses. The interesting thing about two-way ANOVA is that it actually is going to perform three hypotheses tests at the same time. First of all, it is going to look at each of the factors, each of the things that we are trying to test, in this case, the plant food and the soil type, separately. So there is one null hypothesis for each of the two independent factors. And of course, each null hypothesis is accompanied by an alternative hypothesis as well. The null hypotheses will be the same as they were for one-way ANOVA. That is to say that all of the means are going to be the same for that factor. For example, we would have a null hypothesis with regard to the plant food. The null hypothesis would be that there is no difference in the mean plant height for each of the different plant foods. Of course, then, the alternative hypothesis would be that there is some difference. We would have a similar situation for the soil type, where again, the null hypothesis here would be that there is no difference in plant height when using different soil types. Of course, the alternative hypothesis for that would be that there is a difference. So there is one null hypothesis for each independent factor. There is then a third null hypothesis, a third test that is being done at the same time as the other two. And that is for the interaction between the two factors. That is to say, we look at whether just plant food isn't having any effect. We look at whether just soil type is having any effect. And then we need to look at it and say, is there an interaction between them? That is to say, does the plant food itself may or may not have a difference, cause a difference in the plant heights. But does the addition of the factor of the soil change that effect? That is to say, maybe plant food A and B and C all have the same effect. But maybe when you change to a different soil type, they have different effects. So that it may be that whether the plant food has an effect or not is dependent also on the soil type, or the other way. Maybe that if we just you look at plant food A, maybe the two different soil types don't have any difference. But if we change to plant food B, maybe we notice there is a difference between the soil types. So that is what the interaction is about. Here, the null hypothesis would be that there is no interaction between the type of food and the type of soil. That is to say that changing one does not have an effect on the other. Of course, then, the alternative hypothesis would be that there is an interaction between them. So we're going to be doing 3 different hypotheses tests, all in the same situation. Now, here's where it gets complicated. Most two-way ANOVA is done with technology because the amount of calculation in it is just extensive. We saw what the calculation was like for one-way ANOVA, and even for small samples, it could get a little extensive because part of it, the most of the problem was in calculating the sum of squares for the different samples. And the problem was that we needed the mean of each sample and the grand mean of of all samples together in the pooled sample. And that ended up requiring a pretty extensive amount of calculation. In this case, we would have to do it not just the sum of squares between the samples. Here we would have to do the sum of squares between the samples split up by one independent variable, such as plant food. So we would have to find the sum of squares between the 3 different plant foods. Separately, we would have to find the sum of squares between the 2 different soil types. And then, just for fun, we would need to then find the sum of squares of the interaction, meaning that we'd have to look at each of the 6 different things instead of just the 3 plant foods without regard for soil type, or the 2 soil types without regard for plant food. Now we would need to look at all 6 of them together. This, and of course, then there is the sum of squares within. That's the error. But that means that we have 4 sum of squares calculations as opposed to just 2 that we had in the one-way ANOVA. So this does get quite extensive. Each sum of squares also is going to have its own degrees of freedom, which means that, again, we have twice as many things to consider in terms of degrees of freedom. And each one of those then is going to result in a mean squares, and then each of those is going to result in a different test statistic using the F distribution. The table is typically set up something like this. The first column is referred to as source. Your source is going to be your 2 independent factors, which in the case of our example here, factor A was the plant food. Your second factor, factor B, which in this case would be the soil type. Now these two are interchangeable, and that's to say that it doesn't matter which one you do first and which one you do second. You just need to do each of them at some point. You then have the interaction, which is usually written as A cross B, AXB. This is the interaction between the 2 factors. And then lastly, we have within. This is referred to often as the error. For each of these, we need a sum of squares. We might refer to these as SS sub A, SS sub B, SS sub A cross B, and SS sub W. I am not going to give the formulas for these because, again, this is typically done with technology because the extent of the calculations here. If you recall from one-way ANOVA, it was the sum of squares calculations that took the most amount of time. Once you had the sum of squares calculations, the degrees of freedom, the mean squares, and the test statistic were all pretty simple from there. But these were the things that were that were typically the things that took the most calculation. So I'm going to, for the purposes of this class, say that these will always be given to you. And that includes on the tests. If this was a more extensive statistics course, I might have you calculate them, or we would be using a more advanced technology that can calculate them for you. The graphing calculator does have the capacity to do one-way ANOVA. It does not have the capacity to do two-way ANOVA. So we will not be able to be doing this by hand. It is not something that we have reliable technology to use. However, as long as we have those values for the sums of squares, the rest of these can be done pretty straightforwardly. The next column is going to be the degrees of freedom. So far, this setup should be seeming pretty familiar because it's the same basic setup that we used for doing a one-way ANOVA. We just see more rows in this table. Now, the degrees of freedom for each of these rows, the degrees of freedom for factor A is little a minus 1, where little a is the number of different levels, as it's referred to, that factor A has. In this case, for the plant food, it would be 3, because there were 3 plant foods. So the degrees of freedom for the plant food would be 3 minus 1 is equal to 2. Likewise, for the second factor, which we called factor big B, the degrees of freedom will be little b minus 1, where little b is the number of types of soil, the number of levels, as it's referred to, of factor B. In the case of soil type, there were 2 soil types. so little b would be equal to 2, and 2 minus 1 would be 1 degree of freedom. In the interaction, as AXB would imply, it's sort of like A times B, and in fact, that's what we do with the degrees of freedom. We're going to take A minus 1 and B minus 1 and multiply them together. For the degrees of freedom within the samples, this one is a little bit weirder, but it is AB times n minus 1, where again, little n is the size of each sample, the number of items in each group. Where remember, what the requirement was that all of the groups had to have the same number of data points in them. After degrees of freedom comes the mean squares. The mean squares are always found, just like with one-way ANOVA, by taking the sum of squares divided by the degrees of freedom for that factor. So we would take, quite literally, the sum of squares for factor A divided by the degrees of freedom for factor A, and that would be our mean squares. Same thing for factor B. The mean squares for factor B would be the sum of squares for factor B over the degrees of freedom for factor B. The mean squares for A cross B would be the sum of squares for A cross B divided by the degrees of freedom for A cross B. And the mean squares within the samples would be the sum of squares within over the degrees of freedom within. And then that leaves the test statistic as our last thing. All of these things, the sum of squares, the degrees of freedom, and the mean squares, are all necessary to be able to calculate the test statistic. And we will have 3 test statistics. One test statistic that will apply only to factor A. That is our hypothesis test on factor A alone. One test statistic for factor B. That will be our test on factor B alone. And then one test statistic for the interaction A cross B. As with the one-way ANOVA, there is no test statistic for the within the samples. The test statistic is, as before, it is equal to the mean squares for that factor over the mean squares within. These are what we need in order to do our hypothesis tests. It's important to note that there may be different critical values for each of these because they may have different degrees of freedom. The critical value for the F-test is always found with the degrees of freedom of the numerator over the degrees of freedom of the denominator. So while all of them will have the same degrees of freedom in the denominator, they may have different degrees of freedom in the numerators depending on the values of little a and little b. So we have 3 different test statistics, and each one may have its own different critical value. This is a lot to throw out there. As usual, it very much helps to have an example. We're going to use an example I'm pulling from a textbook that talks about the about two different types of paint, and how long they last. Excuse me. The lifespan of different types of paint, the two types we will be looking at is enamel and latex. Enamel-based paint and latex-based paint. And when we say lifespan, it refers to how long before the paint starts to peel and chip and flake off. And in this case, it's measured in months. Now, the second factor is going to be based on geography. In different places, there are different factors such as humidity, temperature, moisture, rainfall, things such as these. So the way this is done is it is broken down into 4 different regions of the United States. Those 4 regions are quite simply north, east, south, and west. So what we have here are 2 different paints, 4 different regions. In fact, to give you the actual data that would be used here if we were doing the full calculations by hand, we would break this down into a table so that we have the enamel and the latex as one factor, as the 2 levels of the factor of paint type. And then we would have north, east, south, and west as our 4 factors for location. In each region, with each type of paint, 5 different samples were taken, or 5 different sets of data were taken. So in the north region, 5 things were painted with enamel paint, and the time in months was measured before they started cracking or peeling. One of the houses had 60 months, another 53, another 58, another 62, and another 57. Of the ones with latex paint in the north, we had 36 months, 41 months, 54 months, 65 months, and 53 months. In the east region, the enamel paint lasted for 54 months, 63 months, 62 months, 71 months, and 76 months. The latex paint lasted for 62 months, 61, 77, 53, and 64. In the south, the enamel paint lasted for 80 months, 82 months, 62 months, 88 months, and 71 months. The latex paint lasted for 68 months, 72 months, 71, 82, and 86. In the west, the enamel paint lasted for 62 months, 76, 55, 48, and 61 months, where the latex paint lasted for 63, 65, 72, 71, and 63 months. Now, this is a lot of data, and if we were to calculate the sum of squares for the factor of paint type and the sum of squares for the factor of geographic region, and then the sum of squares for the interaction between the two, as well as the sum of squares within, we could be here for quite some time. And that's why those sum of squares values will be given to us. However, I did want them here, the raw data here, so that if you were able to use a computer system to do this, you would be able to verify the numbers that are produced. Now, before we run off and start doing other stuff, we have to lay out our hypotheses. We also need to establish a value of alpha. So we're going to test the effects of paint type and location on the lifespan of the paint. And we're going to do so at alpha equals 0.01. The hypotheses then are first for paint type. Our null hypothesis is that there is no difference in the mean lifespan for different paint types. Of course, the alternative hypothesis then is that there is a difference. We also are going to have our geographic location, where again, our null hypothesis will be that there is no difference in the mean lifespan of the paint for different locations. And of course, the alternative hypothesis then would be that there is a difference based on the different location. Now, just to kind of, again, recap with hypotheses tests, you can't just go by what the data looks like. That is to say, if we look at, say, in the North region, the enamel paint seems to all be in the 50s and 60s. In fact, aside from the 53, it seems to all be pretty close in the upper 50s, lower 60s. Whereas the latex only has one value in the 60s, and all the others are in 30s, 40s, and even lower 50s. I would certainly expect a lower average, a lower mean for latex paint than for enamel, just in the North region alone. However, we're not looking at just in the North region. We're looking at all of them. So when we are doing the hypotheses for paint type, we're looking at all of this together versus all of this together. And suddenly, maybe they don't look so drastically different. Now, they're obviously not the same. I mean, at a quick glance, I'd say that we seem to have some more obviously higher numbers on one side than on the other. However, remember that with the hypothesis test, it's not saying that they are absolutely the same. We know that they're not going to be absolutely the same. The question is, are they different enough to disprove the null hypothesis? That they obviously are not, there obviously is some difference, but if the difference is small enough, then it's still acceptable. It's only when the difference is drastic enough that we then say, okay, yeah, it's unarguable, there is a difference here. We get the same thing when we look at it by location. If we look at the longevity in the north compared to, say, the longevity in the south, we definitely see, unarguably, much larger values in the south than we do in the north. And that's just picking out two regions. We also have east and west to consider as well, but my point is that, yes, we look at them and say, yeah, well, I notice a difference there. The question is, in the hypothesis test, though, is not whether there is any difference at all, but whether that difference is large enough to be important in what we're doing. We have one remaining hypothesis then, set of hypotheses, and that is on the interaction between them. And that is to say, instead of just looking at paint type and not caring about location, or instead of just looking at location and not worrying about paint type, we now need to consider both at the same time. So where when we were talking about paint type, we basically had two groups, because regardless of region, we looked at all of the enamel paint. And regardless of region, we looked at all of the latex paint. Now we need to look at all 8 of these, and there are 8 different groups. There's 4 different locations for enamel, and then 4 different for latex, and for a total of 8 total groups. So now we would need to look at the 8 total groups kind of all as individual groups and find the measurements for them. So this one, this null hypothesis is going to be that there is no interaction. That instead of looking at just the enamel versus latex, or instead of looking at just north versus east versus south versus west, we now need to look at all of these as individual so that each group is determined by both factors. And again, the idea here is that we start with the idea that there is no interaction. That is to say that if we are looking at enamel paint, that we're not going to see a difference between the different regions. If we're looking at latex paint, we're not going to see a difference between the different regions. Or the alternative hypothesis, that there is some difference. That there is an interaction between them. So these are our hypotheses. And again, the test is always testing the null hypothesis. So these are our 3 hypotheses that we're going to be testing. And we're going to manage to do all 3 of them, to test all 3 of them basically at the same time with our table for the two-way ANOVA. So we're going to have here our source, our sum of squares for that source, our degrees of freedom for that source, our mean squares for that source, and our test statistic for that source. Our sources are paint type, location, paint type crossed with location, if you don't mind the abbreviation there, and then within all of the different values. Now, as mentioned, I'm going to give you the sum of squares here. The sum of squares for paint type is 12.1. The location sum of squares is 2501.0. The sum of squares for the interaction is 268.1. And the sum of squares within is 2326.8. So these are given. The rest we can determine. The degrees of freedom is going to come from how many different types of paint there are, minus 1. So the degrees of freedom for paint type is 1. The degrees of freedom for location is going to come from how many different locations are there, minus 1, which gives us a degrees of freedom of 3. The degrees of freedom for the interaction is going to be the product of the degrees of freedom of the two different factors. So the 1 from the degrees of freedom for paint type times the 3 for the degrees of freedom for the location. And then lastly, the degrees of freedom within is going to come from the number of types of paint times the number of types of location times the size of each sample minus 1. And that's going to give us a total of 32. Let's give ourselves a little bit more space here. Now, for the mean squares, it's simply a matter of taking the sum of squares for that factor divided by the degrees of freedom. So in this case, 12.1 divided by 1, which of course simply is 12.1. For the location, it would be 2501.0 divided by 3, which gives us a pretty large number, 833.66 repeating. For the interaction, it would be 268.1 divided by 3, which gives us 81.36 repeating. And lastly, for the mean squares within, it's 2,326.8 divided by 32, which gives us 72.7125. Now again, it is common to round because nothing in statistics is absolutely accurate anyway. Everything is kind of a best guess. So we may choose to round some of these longer decimals, like the mean squares within. We might choose to round that and call it 72.7. Or we might choose to do the mean squares for the location and make it 833.7 and round it to 1 decimal place, or even to 2 decimal places. How accurate we need it to be is going to come down to if our test statistic is very, very, very close to the critical value, then that accuracy is going to be important because it may affect whether our test statistic ends up in the rejection region or not. That being said, we really only need to worry about that if it's very, 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 very close, and that's rarely the case. So let's take a look at our test statistics. Our test statistic for the factor of paint type is going to come from our mean squares value, which is 12.1, divided by the mean squares within. So in this case, we're taking the mean squares of the factors divided by the mean squares within. So 12.1 over 72.7125 And that's going to give us a very small value, 0.0166, etc. Now that's small enough. Chances are we don't have to worry about about crossing over the threshold into our critical value and passing our critical value. So if we had used 72.7 and maybe got a slightly different value, it still would have worked out just fine. I'm going to, for the sake of ease here, round this to 833.67, and we're going to divide it by 72.7125. And that's going to give us 11.465. And that's a noticeably larger test statistic, so we may get something going on there. Then we have 81, excuse me, that should be 89, not 81, 89.36666, which we'll call 89.37. Divided by 72.7125, which gives us 1.229. These then are our test statistics. So let's look at each of these one at a time. Paint type. We have a test statistic of 0.166. To get the critical value, we have to go to the F table for alpha equals 0.01. Let's not forget that. That alpha is equal to 0.01, so we have to go to the 0.01 F table. Now, the degrees of freedom of the numerator is 1. That comes from this, because the 12.1 forms the numerator of our test statistic. The degrees of freedom of the denominator then, well, the denominator, 72.7125, came from the within. So the degrees of freedom of the denominator is 32. Now, that gives us a very slight issue because the tables tend to go directly from a degrees of freedom of 30 to a degrees of freedom of 40 for the denominator. So we don't actually see the degrees of freedom for 32 in there. That being said, if we take these two, if we were to use a degrees of freedom of 30, we would get a critical value of 7.56. And now that's using 30. If we were to go to the next one in line, which would be 40, we'd get 7.31. So the truth is somewhere in between there. The idea is that the larger the degrees of freedom in the bottom gets, the smaller the critical value gets. So the actual critical value we would need here is a little smaller than 7.56. However, regardless of which one of these we use, I think it is quite clear that our test statistic is considerably smaller than our critical value. So for the paint type, we would fail to reject. Our conclusion then would be that H sub O for paint type, which said there was no difference between the different paint types, and that the different paint types had no effect on the lifespan, well, we fail to reject that. So our conclusion here would be that there is not enough evidence to reject the idea. There's not enough evidence to reject the null hypothesis. Therefore, we would conclude that there is no significant enough difference between paint types. Next, let's move on to location. Our test statistic here was 11.465. The degrees of freedom of the numerator here was 3. The degrees of freedom of the denominator is 32 because, again, we are always dividing by the mean squares within, which has a degrees of freedom of 32. Once again, we have the same issue with the table, where 32 is not actually listed there. So if we go with 30, we would get a critical value of 4.51. If we went to the next level of the table, which would be a degrees of freedom of 40, we'd get 4.31. So the actual critical value is somewhere in between there, somewhere a little bit smaller than 4.51. However, considering our test statistic, our test statistic is noticeably larger than either of these. So even though we don't get the exact critical value in there, we know that the critical value is close to 4.51, and we are definitely exceeding it. So our conclusion here would be that we do reject H sub 0 for location. We would then say that there is enough evidence to reject the claim that location makes no difference. So far, what we've seen is that, based on our sample data, the type of paint does not seem to make a difference in terms of how long it lasts. But the location definitely seems to make a difference as to how long it lasts. And then, lastly, we have the interaction. The test statistic for the interaction is 1.229. The degrees of freedom for the numerator here was 3, and the degrees of freedom for the denominator is, as it has been, 32. So please note that in this case, we actually end up with the exact same degrees of freedom here as we did for location, which means our critical value is somewhere between 4.51 and 4.31. Now, even though we don't know exactly what it is, our test statistic here is 1.229, and that is certainly smaller than whatever our actual critical value is. So our conclusion here is to fail to reject H sub O for the interaction. Now, H sub O for the interaction was that there is no interaction. So we're going to say there is not enough evidence to reject H sub O for interaction. So again, H sub O said that there was no interaction. And we're saying we can't reject that. So we are saying that we believe there is no interaction between paint type and location. What that means for us is that we can consider paint type without having to worry about location. That they don't interact enough to say that, hey, we need to take into account location when we're picking paint type, or we need to take into account paint type when we're considering our location. We don't have to do that because there is not enough interaction between them to say that each one affects the other. This is two-way ANOVA. It is a process. It is definitely a process. It takes a lot of time to do this, and this is even with me giving you the sum of squares values. To actually have to calculate each of those by hand would be very time consuming. So this being said, this is why technology is used for a lot of statistical analyses, because as you've seen throughout this semester, the calculations are getting more and more complex. We went from confidence intervals, which were relatively simple. You might not have thought so at the time, but they certainly appear that way now, to hypothesis tests for one sample, which had not horrible, but somewhat complicated at times formulas for their test statistics, to two sample hypothesis tests, which certainly had much more complicated formulas for their test statistics. And then we went into ANOVA, which had a lot of calculation just to fill in the sum of squares between and the sum of squares within. This is even worse. There are twice as many rows in the summary table, and the calculations for sum of squares are even more complicated because we simply have more stuff going on. I mean, this wasn't even a particularly large thing, and we had 8 different groups here. That's a lot of numbers to be working with. And that's a lot of means to be calculating for each group, means to be calculating for each factor, means to be calculating for the entire thing. That's what we call the grand mean. This is a lot of calculation. And this is why these things are typically done with a computer program, because to actually crunch all this stuff by hand is excessive and, quite frankly, unreasonable in this day and age, given that we do have computers. So that being said, that's why the sum of squares is going to be given to you. Determining the degrees of freedom, determining the mean squares and the test statistics is certainly something that is within the realm of possibility for what we need to do.